Hello, I am Colin Rothwell. I'm a first-year PhD student in the Computer Architecture group at the Computer Lab, and one of the things we are doing is looking at taking security, which is normally a concern of software in computer systems. You've probably all installed a virus scanner, and actually making that part of the hardware of the system. Why are we doing this? Well, of course, computer security is a massive concern. We trust our computers with so much. We trust it with credit card information. We trust it with, of course, passwords. We trust it with who we stalk on Facebook. Lots of private information can get leaked. We're seeing things like the Heartbleed Bug, which I think is the first ever security vulnerability to be given its own logo. So, to understand how you build a secure processor, I'm going to first go over how you actually build a processor. A processor is just a little device which manipulates a list of numbers. This list of numbers is the computer memory. You can see we start from 0 and we go up to 4. Everything starts at 0 in computer science. Trust me. So what sort of thing can the computer do? Can the processor do? Well, it can take two numbers in, it can add them together, it can output them, and then the new number appears in the output space. How did the processor know to do this? We gave it an instruction. The instruction is another number. In this case, we've shown the instruction in location 4. So why is this mysterious number, 0, blah, whatever, why has this told the processor to do this add operation? Let's break it down. The first field means add. So 1 here might mean add, 2 might mean subtract, 3 might be divide, 4 might be multiply, and so on and so forth. There are lots of different instructions a computer can do. The second part means we add location 0, the third part, location 2, location 1, and the third part means that we put the result in location 2. Obviously, if we want to render Disney's hit motion picture Frozen by writing out a list of numbers, it's going to be really hard work. We've got a couple of things which help us do this. We've got what are called high-level programming languages. These are languages which look more like English, which are easier for a human to program in, which get turned into the lists of numbers. And of course, we just use pieces of code which other people have written. The Heartbleed problem occurred in a particular library of code called Openssl. This is a real problem because of another sort of instruction, which are called pointer or indirect instructions. If we look at an instruction like this, which perhaps means put the thing pointed to by location 0 into location 1, we can see a problem can arise. So what does this mean? Well, you can see that we've looked at location 0 there, and it contains the number 3, which corresponds to a location. So we read a number out of location 3, and then put that into location 1. The problem occurs because any number can be put into 0, and perhaps the user can get 0 into that number, or perhaps it's a library, and we don't trust it. Our solution to this problem is to break up computer memory into different parts. The first part is the normal memory that we've seen before, and the second part is what we call capabilities. You can see these are more complicated, which is a good thing. So, our capabilities start off, we've got one capability which has a base of 0, so that means it starts up at 0, a length of 4, so of course it goes up to 3, because 0 plus 4 it's complicated. And our permission is read and write, and the next capability is blank. The clever thing here is that the instructions we have to manipulate capabilities strictly reduce the permission that we have. So you can't set your capabilities up, hand off to some other piece of code that somebody's written, and then they expand the set of things that they read. So for example, if we were using that instruction before, we're trying to read from location 3 into location 1, but we've used somebody else's code to do that, we could set up our capabilities so that we can read from location 3, write to location 1, and then when we go to that other piece of code, we're sure it's not going to do anything that it shouldn't. It's not going to read your credit card number into location 0, and location 0 gets sent to a nefarious hacker in China. So I'm DARPA funded, so I have a very American mindset on this thing. That is our contribution. That is how you build a secure processor. I've been Colin Rothwell. Thank you very much for your time. Any questions? That's a good question. So computer architecture, the design of processors, is very much a science of trade-offs. When you add something into the hardware, you use space on the hardware, you use up transistors are your sort of basic resource, and you also increase the power consumption. What we're saying is that at the moment, this is a worthwhile trade-off to make. We want to make security easier. We want to make programs that do security less slow in comparison to encourage people to write more secure programs, and we think this is a worthwhile trade-off. Does that make sense?
Before you started the talk, I thought we were going to be talking around the fact that we think of chip design as pretty rigorous, and they pretty well get it right. And software design is not terribly rigorous, with lots of bugs and all the rest of it. And I thought we were going to be using the rigor of hardware design actually to produce the security robustness. Is that a factor, or did I just have it wrong in my vision?
So I think a lot of the reasons that hardware tends to be less buggy than software are actually economic reasons rather than like full personal reasons. Like if you've got a piece of software, what you really want to do is you know that there's a lot of people who are competing with you and they're trying to get their piece of software out. So it's in your interest to write the minimum piece that people are going to buy and ship it as fast as possible so that they're going to buy it and they're going to start being locked into your software. And so you've got the edge over your competitors, and you don't really care about security that much because you can't measure security. You can't say, we've got a secure program, it's just that somebody else has their program out in front of yours. Whereas with hardware, the cost to change hardware, you can't add security into hardware afterwards, or you can't add correctness into hardware afterwards. You've spent like $1 million or way more to build your run of chips, and then it has to go. So you have to be pretty sure before you start selling them that they break, because it's very hard to fix afterwards. Ooh, lots now.
I have a related question. Scalability is a real concern with supercomputers. So, with the hardware amenable to scalability, or reach a point where it's diminishing returns?
In terms of, so, scalability in general is a question with very many facets. We think that this sort of, this capability system will actually help scalability in general because it means you can have more trust between different programs that will run on a system. So you've got to you have like less overhead through checking. So we hope this certainly shouldn't be a limit on scalability, and it might well even help with scalability. That's one of the things I'm going to be investigating with my PhD as it comes. So cool, good question. There at the back.
This is obviously, like, hardware-wise, a fairly significant paradigm shift, other than just the fact that you have to build, like, to have the infrastructure to manufacture these, and, like, are there any other less obvious sort of barriers to integration that you anticipate for something like this?
So one of the nice things about our approach is that it does actually blend quite well. There is actually quite a good ability to shift from old-style, insecure systems to the new-style way. I say that we detach capabilities out in total. That's not quite what we do. We sort of have capabilities as an augment to the old pointer-style stuff, and pointers have to operate through one capability that they're given. So you can have less secure software and more secure software on the system at the same time. And we hope that if this were to be adopted, then people would start writing their secure code for it and eventually would move over to a more secure way of doing everything. So the things can coexist, and this is actually one of the nice things about this.
So if you implemented this hardware, then on the high level, someone would have to design what is sensitive, what is trusted. So eventually, some of these have to bubble up to the high-level languages. Do you think it would make programming in general more complicated? Do you have a plan how it could be integrated in?
So, yeah, the team I'm working as a part of is not just a computer architecture team. It's actually led by a very prominent operating systems researcher. We have a very good compilers guy as well. So this is something that's been thought about right from the start. So essentially, currently we've got modifications to C code that you can add to existing programs, and it's not proved too difficult to modify existing benchmarks to use this scheme. We're also looking at automatic compiler help for automatically adding these capabilities into existing code bases. So there is quite a lot of thought about that, and it is good stuff. I'd quite like to see some more research where we perhaps look at, as you even say, even higher level languages to see if it can help there. I hope that answers your question. Okay, cool.
what kind of specific provision set would you use to prevent something like Heartbleed happening? Would you have a variable event for input potentially, so you can't really say restricts the set of users?
Okay, cool. That's a good question. So the answer is, well, how did we stop something like Heartbleed happening? So I'll try and explain the Heartbleed bug a little bit quickly. The Heartbleed bug was a problem where the user could request more data out than it put in, and some of the data that it requested out could include things like passwords. How we would stop that is the Heartbleed vulnerability happened in a specific part of the Openssl library. We could actually say, before handing off to this part of the Openssl library that somebody else had written, we can say you can only get input out that the user has put in. This is sort of a high-level overview. We actually looked at the Openssl library to see how applicable this is, and it turns out Openssl is so badly written it would be quite difficult to apply this. But having a thing which encourages well-written code to begin with is nice as well. Thank you very much.